Yes. So I'm going for next topic called sample size calculation in survival analysis. Uh, what happened? See, survival analysis, we always talk about the persons in survival, as you say, that persons are survive or not. Means in oncology, the primary outcome to understand the person's uh, um, survive or not. You are giving any therapy, treatment, regime, and trying to find out the efficacy, efficiency of that treatment by looking how many months, year the person survive. So, question is that why this is a different than other study design or objective? Because while you are talking about in other study design, while you are talking about that this number of patients are need to be required, like Dr. Rashid already mentioned that 300, 3,000, 2,000, or whatever the number you said, you are always assuming that these persons are going to be recruited and going to be followed certain number of time. And while you are going to follow them certain number of time, and that time every time they are going to appear and you are going to measure their outcome, they are measured others factors, and you are going to conduct the study. One of the existing problem even in that follow-up study also, because that he mentioned that loss to follow-up is one of the point. Here also in oncology trial, loss to follow-up is a tremendous challenging problem, because many people we don't trace where they are going, we don't understand. What about the current scenario? We don't know. So that is the one existing challenge, and loss to follow-up is always be there. But in addition to that, that is a practical challenge, I would say. The loss to follow is a practical challenge, study design point of view, that is a challenge, and that can be handled by, if you know that 20%, 30% or 40% even patients are going to be lost, so you can make an attempt, you can add more number of 40% addition to your sample size. So if 40% get also lost, so you can cover it up by having. So if your sample size calculation saying your sample size is need to having sample size is 200, but you know that out of that 200, 20% are going to lost. You are not going to get their data. So how we can handle the 20% of 200, that is 40 individuals. So 40 individuals you can add over them. So rather than going for study with 200, you can go for 250 persons and conduct the study. So that would be covered. If 40 people also lost, still you are in a better place to come up with a 200 sample size. So that is the existing challenge. That is a practical challenge that's happened with the sample size calculations or conducting a study. That is a loss to follow. That is always exist in the survival analysis of oncology trial as well, in the phase 3 and phase 4, or let's say for phase 3 I'm not talking. Now in phase 3, that is always existing over that. You can't avoid that kind of challenge. In addition to that, another challenge is always exist, that is the patient died. Because here it's not that patients are all are going to be lost. Many people are going to die. While people are going to die, you are just reducing the number from the study design. So let's say you're going to conduct the study. You said my study design will be 2 years. And out of that 2 years, let's say within 1 year, 50% per people or 50 pupils or 100 people or 50 people, whatever it is, or certain percentage people die. In that sense, you are not going to have a next 1 year information of those 50 or 100 individuals. So that makes a tremendous reduction of the impact on the sample size. So sample size derivations in survival analysis context or oncology context, for particularly for the phase 3 study context, is little complicated, and few steps are need to be there. The common principle like alpha, beta, and delta works, but they are not sufficient enough to work to bring the calculation. So my intention of this presentation is to make what ingredient you need to capture or keep it in mind while you can calculate your sample. I'm sure now at a Google days, YouTube days, you can Google it. So many softwares are available calculating the sample size. You can go to YouTube. So many instructions are given. You can calculate the sample size. Typically for survival analysis, phase 3 oncology trial, it's not a big deal. Big deal is that what background informations are required, what things need to be keep it in mind while you are and need to be given emphasized while you are going to calculate the sample size. That is the most important part. That I'm trying to make it over here. So p-value from the log rank test to check whether two groups differ with respect to the survival hazard. So the basic principle or idea for conducting a phase 3 conclusive trial or in the context of the survival is that you are going to calculate the p-value and the anticipated that the p-value obtained is going to be significant in terms of the comparison between two groups median duration of survival, two groups survival percentage of the survival. So two things can be compared and you are going to make a log rank test over there and going to get the p-value. So this is the basic way. When next week when we go for completely for survival analysis, then we will touch more on the log rank test and p-value. But just for the timing, I'm just saying that log rank test work over here and we can calculate the p-value. One reason such tests are useful is that provide the objective criteria and statistical significance around which plan out of a study. And obviously it gives us requirement of the how many subjects need to be recruited, how many subjects are needed, how long study should be completed, the censoring mechanism need to be considered, and particularly the survival distributions of the null and alternative hypothesis are always required. So first one need to understand that what the survival distributions we are talking. If we are in a positions to find out the survival distribution, typical particular survival distributions, then we are in a better shape. So then we can go for the parametric model, survival model, and you can, or you are not, then we can go for semi-parametric log rank test. It allows us to determine the number of days required to meet the power and design of the study. Secondly, most also it estimates the number of patients that need to be entered in the trial to produce the required number of days. It assumes that the patients entered in a trial over a certain accrual period length and the follow-up of an additional period of time if known as the follow-up time. Patients still alive at the end of the follow-up date, those are censored. We'll describe the sample size because single arm trial and two arm trial here. So important point to be noted. So here we are talking about the sample size calculations for survival data and survival data, how this is distributed, that is very much important. If you could identify the particular type of distributions like Weibull distribution, exponential distribution, that is good. If you don't know, then there is a semi-parametric approach or log rank or non-parametric approach work, and that settle our sample size calculation. Secondly, while you are calculating the sample size, you have to keep it in mind what is the death rate is going to happen, what is the accrual period, because once we are talking about a sample size calculation study design, if you want to conduct a study design, let's say for 5 years, we split these entire 5 years into two parts. One part is this basically dedicated for accrual the patients. So that could be, let's say, 2.5 years or 3 years. And after 3 years or 2.5 years later, we stop the trial from recruiting the patient, new recruiting the patient. Only those who are recruited, we just follow them for next couple of years, next 2 years or 2.5 years. So entered study durations in this context separated, split into two parts. One is accrual period and another is follow-up period. Now, if you're dealing with some studies like, like breast cancer, what is having that mostly in most breast cancer or BMT, that survival rate is very, thankfully, that is very, very good. In that breast cancer cases, you have to have a prolonged survival time. Unless and until you are giving ample opportunity to persons to appear with follow-up time, let's say 5 years, 7 years, 8 years, none of them are going to have any relapse or any death or progression, anything. So in that context, you have to have a follow-up time is longer than your accrual period. Obviously, it does mean if you are having a 10-year study, planning a 10-year study or 8-year study, so your accrual period should be within 2.5 years or 3 years, at the most 4 years, that is very risky. And rest 4 or 5 years, you have to dedicate it to only to follow up the patients. But if you talk about other kind of study like lung cancer, so very, very fast people do progress and die. So here 3 to 5 months, 6 months, or 1 year is more enough. So in that case, you need no need to worry about too much about follow-up time period. You can give much more emphasis on the accrual period. You can give an out of 1 year study if you want to conduct. At the most, you can give 6 to 7 or 8 months even for your accrual period. Rest 2 to 3 months you can allot for the follow-up period. That's the way, because you have to look about the median survival duration, particular site of the cancer you are looking, and based on you have to decide. There is not any way to calculate the particular formula, but you have to, it's a in a trial and error methods you have to decide. So this is the two part of that, and accrual and follow-up period specifications, and simultaneously that death part, censoring mechanisms, how good your data, how your patients are clever and intelligent and coming again and again. That's also important. One of the fundamental approximations for survival data is that the exponential data. I would show why we always go for that exponential data, but blindly we can go for the exponential data. Even if your data is not following exponential distribution, still we can go for that and you can calculate the sample size. Let us assume that we have the constant hazard ratio. So exponential distributions follow that constant hazard ratio form. Other work in literature has indicated the power sample size obtained from assuming constant hazard is fairly close to the empirical power of the log-rank test, provided that the ratio between two hazard function is constant. So, like Ashish told, that once you are having success rate or the dichotomous data or continuous data, we concentrate only the proportions, or it's a continuous data, we can consider the mean or median durations. But here we are talking about the hazard rate or hazard ratio. So the fundamental principle is that we are having two group of people, one group treated with the one drug, and we are going to say what is the hazard rate, means what is the death rate is going to have in this group. And in another group we are also having, they are also giving another type of drug, and we are also going to see what is the hazard rate of this group, and we are going to make the hazard rate comparison between them. Primarily we are making the proportion wise comparison, because rate is nothing but the proportions going to have, but these hazard rate are going to compare. Sometimes this hazard rate also converted into the hazard ratio, so don't be confused on that. So if one group is hazard rate is 40%, another group is having hazard rate as a 50%. So 40% by 50% will by like 4 by 5, or that is around 0.8 would be your hazard ratio. So sometimes in the software you can ask to have to give the hazard ratio. So very cautiously you have to put it's a 0.8. What does it mean? How 0.8 is coming? If is one group anticipated hazard ratio is 40%, another group is 50%, then 40 by 50 you are going to get 0.8. But it can completely reverse your calculations of the sample size. If you go from 0.8, then you can go for 1.8, because if you make 50% divided by 40%, you are going to get the different value. 1.25 is going to have, or what is going, if you divide 5 by 4, what is going to have value? I think 1.25 is going to be your hazard ratio value. Yes, 1.25. So you have to understand which drugs or therapy you are going to consider as a reference group, and which one you are going to have as a treatment group. And based on that, you have to calculate the hazard ratio. Most commonly, the reference group are being considered in the denominator, and the numerator is considered as the best one, and based on that, you calculate the hazard ratio. So hazard rate converted into the hazard ratio here, and based on that, we some software somewhere we calculate the calculations. Now, why we consider the exponential? The reason is that you have seen this, the left hand side, curve, you are always a graph, you are always have seen that this is the way the survival analysis or curves going on. So once you are having a new number, all the patients are started, and then slowly when days passes, month passes, this number of people are keep on decreasing, and they are getting more number of days, and this way within 30 months all of them are died. This is a typical survival analysis curve. And if you see, mostly survival curves looks like this. It shows this pattern. if you reverse this curve, you are going to get some extent with the hazard ratios or the cumulative hazard ratio with these exponential formations. So that's why the exponential is the best choice to have in the survival analysis or data distribution. So by default, you can assume, but some extents it's never happened like similar way these survival curves drop down. Sometimes it stand here and then drop down. Sometimes it's sharply dropped and then it stand there. So several kind of curves you can get here. Based on that, how the graphs are look, it is better to decide the suitable data distribution. But suitable data distributions comes later, but because you're talking about the sample size calculation, so you have to have the anticipated distribution. So in that sense, we are in a better positions to consider survival distributions is going to have an exponential formation. There is nothing wrong to consider exponential as a by default survival distributions, and you can calculate the survival averages. Any comments are there? Okay. What is the variation in HR over time between two groups? That the log-rank. Binod asks, what is the variation in the HR over time between two groups that the log-rank test takes as normal? Okay, variation in HR over time, two groups that I can say that variations means takes as log-rank takes as a normal, means constant. Okay, so basically the fundamental assumption is that the hazard ratio, that's mean the ratio of these two hazard traits should be remain same over there. Some extent, if it is not, if it is ups and downs, if it is changed for particular time, still log rank test can be done. But we will come more on this part later or next week on that. So what is the approximations? But basically, when you are going for the exponential assumptions of the survival curve, so we assume that there is no censoring. There is a special case. There is no censoring. Then we assume that for ith individuals, so particular individuals, survival time is following exponential distributions with particular hazard rate, that is a lambda here. That's all. Now, once you are keep on adding new patients, they are also going the exponential distributions. So by default, all patients are going to have the exponential distribution. These slides make sense that on. And now this one also gives us the opportunity to calculate the variation in the data, likelihood on the data, and finally calculate the sample size on the data. These are the all background reason on that. But exponential distributions work that it says that mean is 1 by lambda and variance is 1 by lambda square. So once why you have to need to know this, because once you apply any software to calculate the sample size calculations, you have to give the lambda value. If you give the lambda value, or it might ask you put the mean value, mean exponential value. So if you put the mean exponential value as lambda, then it would be wrong. It would be 1 by lambda. So if it asks put the standard deviations value, variation of the value, if you directly put the lambda square value, that would be wrong. So you have to keep it in mind what should you going to put while you are going to calculate the sample size. That's why these are required. Not going more details on that, but however, that is our particular satisfactory due to lambda terms in the variance, which means that we will have to solve nonlinear equation. There are so many background, there is so many mathematics are there. I'm not going into details, but these are fundamentally things that what you are going to make. So there is a very confusing scenario always occurs to choose the lambda value or 1 minus lambda or 1 by lambda value. So if you are talking about the mean value, then you should go for 1 by lambda value. Now let's come of the single arm study value, single arm study sample size calculation. So assume that the survival time follow an exponential distributions with hazard rate HT at particular time point age as a lambda, and survival distributions is prepared with the exponential form like that. It's basically a function. Don't worry, it's a function only, and it's following particular distributions. What is our hypothesis? Our hypothesis is that lambda is basically lambda is equal to lambda naught and lambda a, and alternatively we say lambda is equal to lambda a. So basically we are expecting that our groups or single arms, because we don't have the comparison arm, we are having a single arm. So we say that our group of people will be having 40% hazard rate after 3 years, and we can also say no, it should not be 40%, it should be only 20%. So if we say the 20% as an alternative, then a lambda is going to be at 20% here. So lambda is going to be basically 20% or 0.2, and lambda naught is equal to 40%, or like lambda is going to have 0.4. So these are the scenario, these are the assumptions over there to calculate the sample size. So once we are having, then we are going to find the delta. Delta is the hazard ratio between lambda a and lambda naught, and obviously we should be cautious. You are going to put the lambda 0 as a reference or lambda a as a reference. So that's completely changed if the sample size calculations formula. But ultimate goal is to determine how many patients we need to detect certain hazard ratio delta with a specific power and significance level. The principle is like same, like if you increase your difference value, like difference means delta value I'm talking, delta is nothing but ratio value if you say, or delta naught minus lambda naught minus lambda 1. So basically the two hazard ratios difference, if you talk, if your difference is high, obviously your sample size is going to low. If your alpha value is certain, if your alpha value is more, obviously your error value is low, obviously your sample size is going to be high. If your power is high, your sample size is going to be high. So this principle always occurs and appear here as well. But only thing is that we are twisting the proportions value P1, P2 that some Ashish mentioned. Now we are mentioning as a lambda 1 and lambda 2 and by delta value. That's all. These are the basic principles. So these also help us to calculate the number of pupils need to be died, and number of people are total patients number. So that comes up with the MLE estimators, and it also gives us the variations to calculate the variations on that. Another important point here that survival calculation, sample size calculations for survival analysis, we consider in two ways. One thing is that we try to find out how many people need to be die while you are going to end the study, or how many people. That is the one way to calculate the sample size. So while we are talking about more about the hazard ratio or the lambda, there we are going to say how many people are going to die, or how many people are going to have getting the event. So if you say that in my study, whatever number of patients I am recruit, I am going to say conclude the study when, let's say, 400 people are died. So if your study takes 5 years, 6 years, 7 years, whatever the study, you are not worried about the duration of the study. Once you're all recruited, out of all recruited patients, obviously number of recruited patients should be more than 400, then only you can get 400 people die. So once you settle that 400 people died, then you are concluding and going to end your study. This is the one way to calculate the sample size for survival analysis, or make a promise that how many people are recruited. Other way of the sample size calculation for survival analysis is that you are going to make, look, I am going to recruit this number of patients, like 500 patients, and I am going to follow them for 5 years, and out of that 3 years is a accrual period and 2 years is a follow-up period, and that's all. So I am not worried that out of these 400, 500 or whatever the number I'm assuming, all of them will die or not, or how many of them will die, I don't bother. I am going to conduct a study for a particular time point with particular number of people. Once my duration is over, I am going to end the study. Okay, so this is the second approach to calculate the sample size, or way to make the presentation. So only you give the time and how many patients you are going to make. Otherwise, you can give the number of people are going to see over day. So, but thing is that if you are in a so much, if you, as an investigator is so much busy to conduct a study, and you don't know that you are in a better positions to recruit all patients at a time or not, there must be some overlapping, and sometimes your study may be stuck due to some unnecessary reasons. So in that scenario, it is the better to make a promise that how many days you are going to get once you are going to, before you are completing the study, rather than study duration. Because what happened when you commit your study duration with accrual and follow-up period and say this 5-year study we are going to make, but ultimately what happened that out of these 5 years we have seen not even 10% or 20% patients were recruited. So then it makes no sense. So to conclude a study after 5 years, even you don't have a 10 or 20% patients. So, but you have to give the IC and other why you are keep on continuing the study for follow-up longer durations, because you are not recruiting patient, you are busy with other stuff also. Or maybe 5 years before, what was their intention, primary intention or objective, your objective and study importance being shifted from there to different places. So in that sense, it's very difficult to continue a study in longer time point with that statement. So better, the best one approach I would say, to make a comment on how many days or event you are going to allow, and then you stop the trial based on that. So all around that thing is based on that. Log mean methods is a way that help us to calculate the alpha value and also the z value, that Ashish was mentioned over there. And these are the log mean methods is basically calculating the rejections and alternative hypotheses, and based on that we are going to make this statement. So these methods, so directly we are not going for from that alternative or null hypothesis, the lambda value we put, from there we are going to, or these alpha and z value and beta, they are linked with each other. This is the way. So once that been settled down, once your 1 by beta value is settled down with your null hypothesis or your lambda value with your z 1 by beta value, then we can easily calculate the d value, and d values are basically zb and z alpha, and you can get it. Now softwares are there, you don't need to worry about that, but d is basically coming with this lambda delta value. Delta is basically the difference between two lambda. And remember that Ashish mentioned that P1 minus P2 is a difference. Here also the difference is coming as a D, but with as a delta with lambda minus lambda 2. So there is a package in R also, library CleanFront you can use. It's a widely used package in R to calculate the sample size calculations for single arm study. Suppose that you can explore, there are so many materials in CleanFront. Suppose that we are designing a phase 2 study where we plan a 5 number of people, or we can find a required number of days as 5. So that would give, or let's say that we calculate that sample size calculation. So what we need to put is that x log mean date, that is a function you have to put, and between that only single line, delta value we have to meet. Delta value, you have to put the alpha value and you have to put the power value. That's all. It will give you the this number 37. So 37.6 can't happen. So next absolute value. So 38 days according 38 days can be considered to conduct a study. So simple steps is need to be there. Another approach is the likelihood approach, and it also says about that approximations of the generalization of the censoring patterns. So one of the, that I mentioned, that censoring is one of the things that lost to follow up. So here one way it's considered that the both groups are having equal censoring mechanism, unless and until one group is doing very pathetic, then the censoring could be very high in another group than other. So otherwise we consider the general censoring mechanism patterns here, and it says save us with the likelihood ratio approach for fixed and known parameters. The power of the study is given as 1 by beta, 1 minus beta, where we have chi square value, and then we can calculate the delta value for specified alpha, power, and ratio, and all these steps can be calculated. There is a xp like ratio is their functions, that log mean based approach. Then again you can put alpha value, beta value, power value, and it can calculate our sample size. To get number of date, sample size calculations formula as this: exponential ILR date with function of delta, alpha, and power. You can calculate solution for the likelihood based log mean based approach. Another way to consider. Similarly, this single arm studies is also having the another way you can get for this two arm study. Single arm study, we are having a hypothetical formula, pharmaceutical value of the null hypothesis, and based on that, what is the single arm having anticipated lambda value we do calculate. But in case of the two arm study, we are having that we can make the neck to neck comparison between these two arms. So we can have the S0 and S1, so nothing, and there's a similar by lambda 1 and lambda 2, and we can expect that what is the hazard ratio is going to have here. By the similar way, hazard ratio can be calculated, and rest part are similar way, because the mechanisms are similar. Like we can calculate the MLE value, we can calculate the 1 minus beta value, reformulate and we can calculate the alpha value. Once alpha value, 1 minus beta values are in a place, then you can calculate the sample size. And the sample size calculations is there. This form of n equals to z alpha plus z beta divided by delta square p multiplied with 1 minus p with pi. So this say about that, reformulating the statistical test on that, then you can make the comparison on that. Again, make the comparison also. So one thing is that log rank test. I would again tomorrow next Saturday I will touch on the log rank test and other stuff. So once that has been said, because sample size calculations comes first and followed by the analysis. So here we calculate that proportional hazard assumptions, how the delta values stand over there, and how these variations would be considered. So number of events that we require can be computed using the following functions. So these are the functions. So the simplified form is basically p multiplied with 1 minus p with di. So once you are having two survival distributions, comparisons, so we can make p multiplied with 1 minus p and di. And di and p is basically number of subjects assigned to the control group and over the another group, so in the experimental group. So these are the computational steps. Once p minus 1 by d, the d can be also be formulated like that, standard calculations. So my reason is that, see, all these things are interlinked with each other. So again, once you are going for sample size calculations, you have to keep it in mind that what is the durations over there, how many follow-up study you are going to have, what is the accrual period you are going to have, what is going to have your anticipated alpha, your lambda value of the experimental group. If you are having two groups, then what is the difference between these two groups, and simultaneously alpha and beta value. And rest things are being settled here. And you can and softwares packages are available, and you can make. So this is simple two arms functions over there. My apology if the title is wrong. The two arms date would be the functions as a delta, p, alpha, and power. So you can make that z alpha value, beta value, and number value, and you can calculate. So once you are having settled down these two arm functions, then you can call two arm functions, call as what is my delta value, what is my p value, alpha value, and power. You will get the sample size as 65. Another way, if you from delta 2 to, if you let's say if you increase the reduce the delta value, other stuffs are same, see, mostly same, only we increase the power from 80 to 85, but alpha is same, power p value is same. See, just we shift from delta 2 to delta 1.83. So just to reduce the delta value. So basically we are narrow down the difference between two groups. So once you narrow down the difference between two groups, our sample size inclined from 65 or 66 to 90, 98 basically. So that's the way. So the principles was same. If you are having narrow down the difference between two groups, then obviously your sample size is going to be high. So similarly, way it's happened. Want to compute the probability of death from the non-parametric estimate of the survival terms. Assume that the accrual time is 336 days and the follow-up time is 180 days. However, we can estimate the probability of death pi. The number of patients need to be for trial will be estimated by d by pi, where d is the required number of death. So this is the another functions you can use. So, but these functions basically to calculate the number of death you are going to calculate. That I mentioned that you can, rather than going for sample size or saying how many patients you are going to recruit and follow, you can directly straightforward go for number of days you are going to have, and that is the way you can calculate. However, we can get estimate the probability of death by the number of patients need to be trial. We need to estimate at D is required number of days. Again, the same results would give you the thing. So with that note, I would like to end here. I think we already extended the time and it's long. So any questions, any comments?